Hey everybody, welcome. This video is actually going over a Kepler law that we already learned about in the last video. If you didn't watch that first set, you should, because it's giving an overview of 3 of Kepler's laws. We are actually going to dive a little bit deeper into Kepler's third law. It is also a challenging topic. It is understandable if you walk away from this video being confused or not sure how to solve these problems. We're doing some math. That's why it's good that you are just familiar with what Kepler's third law is saying, and then at least if you're in my own class, we're going to be doing practice and going over this probably the next time that I see you, okay? Now, as a reminder, we already went over the definition of Kepler's third law. What it does is it's comparing how much time it takes a planet to, let's say, orbit the sun or any star, comparing that to how far away that planet is. Meaning, the Earth is closer, it has a smaller distance away from the sun compared to Mars. What we said in the last video was, well, since it has a smaller distance, that means it takes less time. And that's true, everybody. But that's a little too simple, at least in terms of what you're expected to know in our high school physics class. We can go a little more in depth. Kepler's third law is a bit more specific. While we said there is a dependence, that distance and time are related, we did not discuss what that dependence actually is. Kepler's third law, it turns out, it is a proportion. It is a relationship. It's using math to show how similar or how the distance and time relate to one another. And if you're in my own class, we have probably done some proportion practice already. This is arguably, in my high school physics class, the most challenging proportion kind of math problems that we're gonna see. So again, I know this is a tough video. Do your best to follow along, try your best to be familiar, and get ready to do more practice. But I'm gonna go over what this proportion is. We're gonna do an example problem, and then we'll be done, okay? So here we go. Getting a little more specific, we're relating time to orbit based on how far away from the sun we are. The time of an orbiting object, which we're just going to call t, t for time. We use an uppercase t because, again, it's a specific time. It's the time for, let's say, the Earth to go around the sun, and the time for Mars to go around the sun. The time t, it's related to the distance r. We often use r for distance because we're tracing out objects that are kind of circular, and like in circles, we use radius, right? So that's why we use r, all right? The time between, or the relationship between t and r, oh man, it is weird. It is t, time, to the second power is related to r, distance, to the third power. There's a lot going on here. First of all, this is not an equation. Time is not equal to distance. That probably makes sense, okay? So we're not really dealing with an equation, even though we can often treat it like such. We're looking at a relationship. Just like apples are not the same thing as oranges, but they have similarities. That's what we're looking at. There is a similarity between how far away a planet is and how much time it takes. So that's why we're not using an equal sign. This is a symbol often used to represent proportions. And again, if you're in my own class, there's a good chance we already saw this. But also it's weird because both of these have exponents. This is not an easy relationship. The time to the second power squared is related to the distance of the planet to the third power, or I might say t squared is related to r cubed. Weird. This is something that could be graphed, and that's what I'm showing right here. I just went to Desmos and I typed in, I said, hey, take y squared, set that, I used equal because Desmos doesn't have this proportion, at least not obviously, is equal to x cubed. And if you make a graph, you get a graph that looks like this. It kind of looks like one of your parabola graphs that you may have seen in a prior math class. And I also know you're probably more related or used to like graphing y equals x cubed, but you could also square the y. There's no rule in the universe that says you can't. But anyway, this is our relationship, how we relate t and r. Again, if you're in my own class, we actually may have done an activity where we took time of certain objects, let's say to orbit the sun, we raised them to the second power, and in this case we divided to get a number. We divided that by the distance, the radius to the third. And if you did this in my own class, maybe you notice that you get a same or a very similar number each time. That's what this is saying. You have a similar relationship, a similar ratio. There is this relationship between t, when it is raised to the second power, and r, distance, when it's raised to the third power. This is showing, since we got the same numbers, if you did your math right, this is a relationship between those two things. Now, I'm not going to read this full quote. You could hit pause if you want. This is what Kepler found in 1619, okay? Now, in the 1600s, we didn't have the most amazing telescopes or ways to measure time. So if you notice, in his own fractions, they're not perfect, but we'll give them a little leeway just because there weren't amazing ways to measure things. But Kepler did the exact same thing. He had all this data for the different planets orbiting the sun, and he found that, well, when they took the distance and they raised it to the third power, and they looked at time and they raised it to the second power, you get the same fraction. That's him discovering this relationship, okay? T squared is related to r cubed. Now, this is not important for us, as you'll see in a second why. Isaac Newton, almost 100 years later, used Kepler's data, and Newton was admittedly a genius. He went a step farther. He actually found the actual equation, and oh my gosh, this is a nightmare. Look how complicated this is. We are not going to use this equation in my class. Thank goodness, it's a lot. But do you notice? There's a t squared here. There's an r cubed here. Just Newton found what the actual equation is. We're just going to focus on the relationship, the fact that t squared is related to r cubed, okay? Also, this is a little tough to analyze written as is because, again, we're raising two things to power, squares and cubes here. One thing you could do, treating this kind of like an equation, is if I actually took this equation and if I took the square root, remember, taking the square root is kind of the opposite of squaring things. So I could actually rewrite the relationship like this by taking the square root of both sides. These are the exact same thing, okay? I just took the square root of both sides. This one is nice because now this just says how much time it takes to orbit is based on this. Or, oh man, and I know this is weird math, it's maybe been a while. If I take the cubic root from both sides, I can solve for r. Again, these are actually the same equation. All three of these, same relationship. All three of these are identical. And probably, if you're in my own class, I'll actually likely give you all three of these. But we're likely going to use these just because it's easier to solve for our proportions, okay? All right, we're going to do an example, okay? Because I know this is weird, and I know even after the example, it's going to be weird. But then we're going to do practice if you're in my own class, and probably if you're in someone else's class or course, okay? We're going to do one of those proportion problems. As a reminder, the way we approach a proportion problem, this is a different relationship. Let's say I have y is related to x squared, and I asked you, what happens if I doubled x? What would happen if I had this relationship? What happens to y if I take x and I decide to double it? The way we learn to do this, if you're in my own class, is we kind of write out the original and then we put in the change. If I double x, that means instead of x, I'm going to have 2x. Here's why I'm putting this in this slide. You need to remember that when we're dealing with exponents, and this is all about exponents, you need to, the rule of math, you need to apply the exponent to both things. Because x is being doubled, I use these parentheses. And the rule of math is, if I'm raising this to the second power, I have to raise both of these to the second power. Meaning, 2 squared is 4, x squared is just x squared. So that's how I go from this line to this line. I have to square both things in the parentheses. So what happens when I double x? Well, notice, in my original, I have y is related to x squared. In my new version, I have also y is related to x squared. Oh, but there's a 4. So what has happened? I have now made my relationship 4 times larger. Now there's an extra 4 in front of my relation. This problem here with Kepler's third law is like what we've done before, kind of on steroids, okay? Now, again, if you're in my own class, you're going to get notes, you're going to see this, and the teacher is going to walk around to help out, but we're going to walk through one of these problems. This is my last slide, okay? Let's learn how to, or see how we apply these proportions to a math problem, okay? It says, Jupiter is about 5 times as far away from the sun as the Earth. The question is asking, how many times larger is its orbital period? I want to know, is the orbital period, that time, is it 10 times bigger? Half as big? That's our question, and I'm going to walk through it with you, okay? You could try it on your own, but I get this is tough. Now, team, first hint, we're going to use one of these versions. This version is great when you're trying to find out what happens to time, because this says t is related, and you mess around with the distance. This version is good when you're trying to find out what happens to r, because it says the distance is related to doing something with time. So, read this problem. Do I want to figure out what's happening to the time, or am I trying to figure out what happens to the distance? Which of these versions am I going to use? Am I going to use this proportion, or am I going to use this proportion? What do you think? I'm going to use this proportion right here. It's asking, how many times larger is its orbital period? So the first challenging thing for these problems is you got to figure out, what is it asking for? Is it asking how the time changes, or is it asking how distance changes? Because in this problem it's asking how time changes. I want the version that has t is related to. Okay? Now, if you remember our proportion kind of steps, let's just go through it, okay? I know it's a more challenging version, but it's the same setup. The first thing I do is I just copy down the original, the OG, the old version, the one that we were first introduced to. It's right here. T is related to the square root of r to the third power. I know that's a lot, but we're just going to go through it step by step. The next thing I do, we're going to change this. According to the question, we're looking at an object that's 5 times farther. So t and t, that's the same, related, square root, but instead of r, I'm going to put in 5r. It's 5 times the distance. That's why I put in a 5 right here. I am now multiplying the distance by 5. This is the distance right here. I'm multiplying by 5, okay? Let's simplify. I'm going to keep the square root. Let's focus on what's going on the inside first. Let's see. Do you understand how I got from here to here? It's just like this problem I went over earlier. If I'm squaring something, I have to square both things in my parentheses. Here, I'm raising something to the third power. And careful, that's not the same as multiplying something by 3. You need to, in your calculator, raise both of these objects to the third power. Use your calculator. 5 to the third power is 125. R to the third power, well, that's just R to the third power. So that's how I get to this line here. I just rose both of these to the third power. 5 cubed is 125. R cubed is R cubed, okay? I'm going to move over here just because I have a little more space over there. And also, what I did right here, this is kind of optional. But I'm just showing, like, the rules of math. I have 2 things underneath this square root. It's okay if you forgot this. This step is not required. But I can kind of separate these. I can kind of factor it out. It's the same thing as if I have kind of the OG, the original, with this square root of 125. I still have to keep that square root in there. What is the square root of 125? I don't know what that is off the top of my head, but I could plug it into my calculator. This is just a number. So I could just plug that into my calculator, and when I do that, I get 11.18. The square root of 125 is 11.18. Now we're basically done. Let's see how I can answer this question. How many times larger is the period? Well, here's the original one, team. The original is, it's related to square root of r cubed. Notice, t and t, that's the same. Related, that's the same. Square root, r cubed. Everything is the same between these 2 equations, except, what's different? This thing. In my new version, I am multiplying by 11.18. So, how many times larger is the orbital period? It's 11.18 because that is being multiplied. It's being times the original. So the answer to this question is the period is 11.18 times as much. Or you could say 11.8 times as big, 11.18 times larger. Any of those phrases work. But that's how I figure it out. Challenging. Absolutely. But it is the same steps, just the challenge is now I have exponents, now I have maybe roots or cubed roots. It's a tough one. Okay, but we'll do practice next time I see you in class, okay? I know this is a challenging video and probably a longer video, but it's a tough topic, okay? Thanks a lot for watching. That's the end of this one. See you next time.